Hello all. Today's lesson is about shapes of molecules and ions. What I'm going to start by explaining is why a molecule has a certain shape. But we must remember what a covalent bond is. So a covalent bond is a shared pair of electrons. And at the bottom of this slide, we can see a molecule, boron trifluoride, BF3. And it has three single covalent bonds. Each one of these single covalent bonds has a shared pair of electrons. And we know that electrons are negatively charged, and electrons will repel each other to minimize the repulsion in the molecule. So these pairs of electrons that I've highlighted in yellow will repel each other so that these pairs of electrons are as far away as they can be from each other to minimize the repulsion in the molecule. That's what gives rise to a particular shape depending on the number of electron pairs you have, or depending on the number of lone pairs and electron pairs that you have. So if we had to explain in the exam why this molecule, BF3, has this shape, that shape is called a trigonal planar shape, what we would write in the exam is the three pairs of electrons repel each other equally, and those words repel each other equally are very, very important, so that they are far as away from each other to minimize the repulsion in the molecule. And then we would go into the shape that's formed and the bond angle that we get. But I'll talk through the shapes and the bond angles as we go through this lesson. The most important thing to remember is that if you have electron pairs, they will repel each other so that they are as far as away as they can be from each other to minimize the repulsion in the molecule. What we'll do is we'll go through all the different shapes we can get. We'll also look at the bond angles, and we'll try to write some of these explanations down as we go through the PowerPoint. So just to quickly recap how to draw molecules. When you draw a molecule, it must reflect the 3D shape of the molecule. Often this is much easier done if you make a model of the molecule using these chemistry model kits. It certainly helps you visualize which way the bonds are pointing. So just to go through this example that you can see on this slide, this is a molecule methane. You've got a central atom and you've got four atoms around it, which are the same, the red ones. So they could be, say, hydrogens. The middle one could be a carbon atom. And what I've done on the right of it is showing you how we would draw this molecule out. So these two bonds, the ones that I've highlighted in yellow, these two bonds are in the plane of the paper. So these are shown by these straight lines that we have. The bond that is coming out towards you, which is this one that I've highlighted in pink, is shown as a wedge. Okay, the wedge indicates that the bond is coming out towards you. And then there is a bond that is going backwards, that one that I've highlighted in blue, and that's this dotted line which indicates that the bond is going backwards, it's going in. So it's very, very important we reflect the 3D shape of this molecule. It would be incorrect to draw this molecule like this, a C in the middle, and then to just draw four sticks around it like that. That does not show the 3D shape of the molecule at all. And instead, we must reflect the accurate 3D shape by drawing it properly. And this is called a tetrahedral shape. Okay, so that's known as a tetrahedral shape. And this certainly would get you your marks in the exam. But we do need to talk a bit about how we draw these molecules and trying to avoid common mistakes when it comes to drawing them. Okay, so this is just a very, very quick recap of what the different types of bonds mean. But hopefully you've seen that in your chemistry lessons. So let's get on with how to work out the shape of a molecule. Then we're going to look at the different shapes of the molecules we get, and we'll try to go through lots of examples just to show you how this works. So I like to use this method. This is one of my own methods of how to work out the shape of a molecule. And for me, it works well every single time, and I've seen plenty of pupils do very well with this method. So the first step is to work out the total number of electrons. To work out the total number of electrons, all you do is you look at the group number of the central atom. So what you have to do first is to identify what is the central atom and what group is it in the periodic table. And all you do is you add the number of atoms around it. So remember, first step is total number of electrons. group number of the central atom once you've identified it, plus the number of atoms around it. If at this point it's an ion, and we'll look at some ions as well later on, if it's an ion, you'll have to add or remove electrons. So if it's a positive ion, you'll need to take away an electron. If it's a negative ion, you need to add an electron. The next thing you do is you divide the answer by 2. And when you divide the answer by 2, this will tell you the number of electron pairs. Okay, so this will give you the number of electron pairs. And then what we do is we work out the number of lone pairs. And to work out the number of lone pairs, we take this answer that we have, our answer from step 2, and we take away the number of atoms around the central atom. So to work out the number of lone pairs, we do the number from the step before, and we take away the number of atoms around the central atom. Now it might seem confusing, and you might need to write this down before we go through the next few examples. You can always come back to this and pause this whenever you want to. So let's have a go at doing this, and let's see how we work out the shape of a molecule. So I'm also going to introduce the different shapes of molecules and the bond angles, and then go through how to work it out, because I think that will stick in your head better, and also it means you can make a note about the different shapes we get on a piece of paper. So the first shape I'm going to look at is this shape here, which is linear. Okay, so linear is the first shape we're interested in. And when we have a linear shape, the crucial thing to remember is we have 2 bonding pairs. So if you get 2 bonding pairs, you can only arrange them in one way, and that's this picture which is in the middle, where X is your central atom, and there are 2 bonds either side. The bond angle in this molecule is 180 degrees. That's the angle between the 2 bonds. It makes sense. If you've got 2 bonds, the electron pairs in these 2 bonds will repel each other equally, so that the 2 bonds are as far away as they can be from each other to minimize repulsion in the molecule. And that's why BlCl3, which we're about to look at, will have a linear shape. So let's look at the sequence that we work out the shape in. So remember, we work out the total number of electrons. So total number of electrons is equal to group number of the central atom. It's fairly obvious, certainly by looking at this particular molecule, that beryllium is your central atom. So if we think about the group that beryllium is in, it's in group 2, okay, plus the number of atoms around it. The number of atoms around it are 2, because there's 2 chlorines around it. And that will give you 4 electrons in total. So that's 4 electrons. The second step was to take this number and divide it by 2. It also did mention something about it being an ion, but I can see straight away it's not an ion, so I don't need to worry about that. So take this number 4 and divide it by 2, and that will give me 2 electron pairs. So 2e minus pairs, shorter way of writing it. The third step, which is the important step, is to work out the number of lone pairs. So LP is lone pairs. Lone pairs, remember, equals the answer you got from step 2. So that's 2. Take away the number of atoms around the central atom. Well, the number of atoms around the central atom is still 2. There's 2 around the central beryllium. So it's 2, and therefore that equals 0. Lone pairs. So therefore, and this is the important part, and you'll get more and more used to it as we go through this lesson, therefore my conclusion is, out of these 2 electron pairs, if none of them are bonding pairs, if none of them are lone pairs, it must mean that out of these 2 electron pairs, I have therefore got 2 bonding pairs of electrons. Okay, if I've got 2 electron pairs, either it's going to be 2 bonding pairs, it could be 1 bonding pair, 1 lone pair. There are lots of different combinations that you can get with different shapes, but the crucial thing to remember is if I've got 2 electron pairs, I have to work out how many of those 2 electron pairs are bonding pairs and how many are lone pairs. Well, if I have no lone pairs, then the 2 electron pairs must be 2 bonding pairs. Then I draw out the shape of the molecule where I replace X, which is my central atom, with beryllium, because that's what my central atom was. So beryllium, I draw 2 single covalent bonds because I've got 2 bonding pairs of electrons. That means I've got 2 covalent bonds, and I put chlorines on the end like that. That's linear shape, so I would make a note that the shape of the molecule is linear, and I would mark the bond angle, the angle between the 2 bonds, and the angle between the 2 bonds here is 180 degrees. And that will get me my marks in the exam. I'm going to move on to the next shape. I'm going to tell you the next shape we get depending on the number of bonding pairs that we end up with, and then see if you can do the same working out and see if you can draw it, and you can just pause the video. So the next shape we have with 3 bonding pairs of electrons is a trigonal planar shape. So this time we have a trigonal planar shape. There are 3 bonding pairs of electrons, and there they are, 1, 2, and 3. You get this nice Mercedes sign, and essentially the bond angle here between them is 120. And it makes sense because if you've got 3 bonds, they will be equally spaced out. Remember that if we had to explain why we've got this trigonal planar shape, we would say the 3 bonding pairs of electrons will repel each other equally. That language is crucial. Repel each other equally so that they are as far away as they can be from each other to minimize the repulsion in the molecule. And therefore the bond angle is 120 degrees. It's a full circle if we think about it. Okay, so we'd have another one here as well, and we'd have another one around as well. So we could get a full circle here, one there and there. So if we add them up, that would give us 360, which is a full circle. But anyway, let's continue with this molecule that we're looking at, which is BF3. So let's have a look at if we can prove that BF3 has a trigonal planar shape. So we'll start with total number of electrons. So total number of electrons, remember, equals the group number of the central atom. So we need to identify what the central atom is. That's the boron here. It's the B. So the boron is in group 3. So 3 plus the number of atoms around it, which is 3 fluorines. So that equals 6 electrons in total. It's not an ion, so we don't need to worry about adding or removing electrons. The second step was to take that number 6 and divide it by 2 to work out the number of electron pairs. So that's 3 electron pairs. Now, what we need to work out is how many of these 3, out of these 3 electron pairs, how many are bonding pairs and how many are lone pairs? Or are they all bonding pairs? The only way we will know that is to work out if we've got any lone pairs. So our next step is to work out the lone pairs, which is take the answer which we've got, which is 3, and take away the number of atoms around the central atom. Well, we've already worked out that boron's our central atom and there are 3 fluorines around it. So 3 take away 3 will give us 0 lone pairs. So therefore our conclusion is out of these 3 electron pairs, all of them must be bonding pairs. Okay, so all of these electron pairs must be bonding pairs. So therefore we have 3 bonding pairs of electrons. There will be occasions where you'll end up with 2 bonding pairs and 1 lone pair, but we can look at these later on in this particular lesson. So if we had to draw the shape of a molecule with 3 bonding pairs, that's the general shape. I'm going to replace X with boron, and I'm going to draw these bonds like that. And there we go. And then label one of these bond angles, and then I'll put the fluorines on the outside. So one of my bond angles there is 120 degrees. Okay, and there's just my fluorines put on the end, and there we go. And that again would get me my full marks in the exam, providing I identify the shape as being a trigonal planar. Okay, moving on to the next shape. The next shape is if we've got 4 bonding pairs of electrons. This is now a tetrahedral shape, and that's 4 bonding pairs of electrons. This is the one I mentioned when we were talking about drawing the 3D arrangement of the molecule, about the wedge, the dotted line, and what the straight line represents. In this case, when we've got 4 bonding pairs of electrons, what happens is the 4 bonding pairs of electrons repel each other equally so that they are as far away as they can be from each other to minimize repulsion in the molecule, and we get this shape here, a tetrahedral shape, which you've got to learn how to draw. And the bond angle in this particular molecule, it doesn't matter where you draw the bond angle, as long as it's between 2 bonds, is 109.5. A rather tricky number to remember, but you get used to it the more you draw this. So let's prove that methane does have a tetrahedral shape. So the first step is to work out the total number of electrons. The total number of electrons is equal to the group number of the central atom. Central atom here is carbon, so that's in group 4, plus the number of atoms around it. There's 4 hydrogens around it, so plus 4, and that gives us 8 electrons in total. It's not an ion, so we don't need to worry about adding or removing electrons. We then take this number, divide it by 2, so 8 divided by 2 gives us 4 electron pairs. Remember, that tells the number of electron pairs. And then we need to work out of these 4 electron pairs, how many are lone pairs and how many are bonding pairs. So to do that, we need to work out the number of lone pairs that we have. And that's take this answer here, 4. Take with the number of atoms around the central atom, so that's 4 hydrogens around it, gives us 0 lone pairs. Now you might be thinking, hang on, why is it that you keep getting 0 lone pairs? That's because we're going through the straightforward shapes at the start, and then we'll certainly go into the more complicated shapes as we get into the rest of this PowerPoint. Therefore, my conclusion here would be that out of my 4 electron pairs, I have got 4 bonding pairs of electrons. So therefore, I've got 4 bonding pairs, and if I draw the shape for 4 bonding pairs, I just simply replace X with my carbon and draw this. There it is, H, 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 and the bond angle, which I'm going to label in blue, there is 109.5 degrees. Now, there is one mistake which certainly has been pointed out by examiners, and that's when people draw this very, very quickly. I'll show you what they do. They draw it out like this. And as you can see, you might say, well, actually, hang on, there's nothing wrong with it, because you've got the 2 lines in the plane of the paper, you've got a wedge, and you've got a dotted line. The problem is, if you look at the wedge and the straight line at the top, they're actually 180 degrees between them. And that's incorrect, because I'm trying to show that the bond angle, actually, if I label it as 109.5, isn't reflected in the way I've drawn it. So you've got to make sure that when you draw it, you do try to reflect that there is that angle in that molecule. So that would be incorrect, because there you can clearly see it looks like 180 degrees, and yet I might label it as 109.5. It's not drawn correctly. So please don't do something like this. Draw it as you learnt it, okay, and make sure you learn it properly so that you don't end up making a common mistake. That could be the difference between a grade. Okay, moving on to the next shape. I'm going to do these a bit more quicker than what we've done previously, because I'm sure you've got the hang of how to work out the shape of a molecule. If you've got 5 bonding pairs of electrons, you get a trigonal bipyramidal shape. Okay, so you've got a trigonal bipyramidal shape. And this time you've got your central atom, you've got a bond going up, down, and a bond going 90 degrees to it. So that's why this bond angle here is 90 degrees. This angle here would also be 90 degrees as well. But as well as you've got this up, down, and one to the left, you've also got a bond coming out and one going back in. And you can see it a bit more clearly with this example here of where those bonds are. Okay, this molecule that you can see on the right-hand side. The bond angles across this plane here is 120. This is almost like your trigonal planar shape, and then you've got just a stick going up and a stick going down, i.e. a bond going up and a bond going down. Okay, but you've got 2 bond angles, 120 along this kind of part here, and then 90 degrees. I'll just try and annotate it a bit on here. 90 degrees between there and also between there. Okay, I'm just going to get rid of that because it ruins what I've got there. So let's prove that phosphorus pentachloride has a trigonal bipyramidal shape. So we need to work out the total number of electrons, which is the central atom, which is the phosphorus. So that is in group 5. Plus the number of atoms around it, that's 5. Gives us 10 electrons in total. It's not an ion, so we move on to step 2. 10 divided by 2 will give 5 electron pairs. Okay, we then work out the number of lone pairs. So lone pairs is equal to this number 5. Take away the number of atoms around the center, which is 5, and that gives us 0 lone pairs. So therefore, we need to write our conclusion, and our conclusion is out of these 5 electron pairs, we actually have 5 bonding pairs because there are no lone pairs at all. So there are 5 bonding pairs. What we now need to do is to draw the shape of this molecule. If we just take this template here, we put X as being the P, up, down, across. These are where my 90 degrees bond angles are, and then we need to draw this kind of trigonal plane arrangement that we get in the other kind of plane. Put chlorines around it like this, and then label my 2 bond angles, so 90 degrees there and 120 degrees here, because that's 120 degrees. Okay, I'm going to move on to my next shape, and I'm sure you'll be relieved to hear that this is the last shape in terms of the standard shapes where we don't have any lone pairs, when we only have bonding pairs. But we'll soon start to look at cases where we have lone pairs in there. So if we have 6 bonding pairs of electrons, we get this shape octahedral. And there are different ways to draw an octahedral shape, but essentially 6 bonding pairs of electrons will repel each other equally, and you'll get this shape here where the bond angle is 90 degrees. So you can draw your up and down, which is what I've got here. You can draw something that's coming towards you, like these 2 bonds are here, and then you've got these 2 going backwards, and you can draw this arrangement almost like a star there. Or sometimes I prefer to draw it in a different way, and this is correct as well. You might prefer to draw it like this. You'll draw a lot of this when you learn about transition metal chemistry, and you can draw it like that, where you've got this X in the middle, and you've got this kind of cross, and you've got a bond coming out and a bond going backwards. It's the one that you're most comfortable with drawing. Both of them are correct. I prefer to draw this one over the one in the middle, but it doesn't matter which one you go for. So let's try and work out what sulfur hexafluoride will give us. Hopefully it gives us an octahedral shape. So total number of electrons is equal to the central atom, which is the sulfur, the group number of it, which is group 6, plus the number of atoms around it, which is 6. So that's 12 electrons in total. To work out the number of electron pairs, you take this number 12 and you divide it by 2. So that will give us 6 electron pairs. What we then do is work out the number of lone pairs. So the number of lone pairs is equal to this number here, which is 6. Take with the number of atoms around the center, which is 6, and that will give us 0 lone pairs. So my conclusion is, out of these 6 electron pairs, they all must be bonding pairs, because I have no lone pairs at all. So 6 bonding pairs of electrons. I'm going to stick to the way that I prefer to draw it. So X is my sulfur. I'm going to draw my bond up, down, across, a wedge coming out like this, and a dotted line like that. Put the fluorines on the end of all of these, and the bond angle in, it doesn't matter where you measure it, as long as you do it right, it's going to be 90 degrees. Okay, so the bond angle here is 90 degrees. Okay, so it's 90 degrees between, it doesn't matter if I that's the one I've kind of labeled on my molecules there, that's 90 degrees there. Okay, moving on. Now the fun part comes on this in this next bit, and what I'm going to do is just slightly modify what I've got, but it's a very, very quick recap of the molecule we've seen. We've seen a tetrahedral shape where we've got 4 bonding pairs of electrons. So here we have 4 bonding pairs of electrons, and we get this tetrahedral shape. But remember, this shape is based on 4 electron pairs. And if out of my 4 electron pairs they weren't bonding pairs, then I'd start to get different shapes. So there will be different situations, we'll see these in a minute, where the 4 electron pairs don't translate to 4 bonding pairs. And what you might get, which is what I'm going to start by drawing to the right, is you might end up with the conclusion that you've got 3 bonding pairs and you've got 1 lone pair. So 3 bonding pairs and 1 lone pair. And when it comes to 3 bonding pairs and 1 lone pair, the total is still 4. All you do is you replace one of these bonds with a lone pair. So I'm going to replace that one at the top with a lone pair. So there's X, there's a bond there, there's another one here. There we go. And the top one I'm going to replace using a lone pair, like that. That little ghost sign, that little circle with 2 dots represents a lone pair. So there is my lone pair at the top, this one here. Now the angle, you can't do between here. It's a bond angle. It's an angle between 2 bonds. That is an angle between a lone pair and a bond. You can't see the angle between a lone pair and the bond. So it's very, very important that you always label the angle between the bonds. And there we go. And when we've got a lone pair, a rule to remember is if you've got a lone pair, then you kind of minus 2.5 degrees from the angle you've got. Okay, one lone pair is about 2.5 degrees. You can take away about 2.5 degrees and you'll work out the new angle you've got. There is a reason why the bond angle is reduced, which I'm not going to go through in this lesson because it will be quite a long lesson, but I can do as a separate lesson if you want me to. But if you take away 2.5 from 109.5 degrees, you're left with 107 degrees. Okay, and we'll have a look at the name of this shape in a minute. We'll talk more about this shape in a second, but I just don't want to put too much information on one slide that we lose the plot. So out of our 4 bonding pairs, we can also get out of our 4 electron pairs, we can get 2 bonding pairs, and we can also get 2 lone pairs. In this case, all we do is we replace 2 of these, doesn't matter which one, okay, as a lone pair. So I'm just going to replace that, and if I squeeze it in this tiny gap I've got, you'll end up with a picture that looks something like that. Okay, and you might say, yeah, but it looks more like this. That's perfectly fine if you drew it like that. So it's probably as best as I can draw it on here, but I'll show you another way of drawing it afterwards. Okay, so you get to this shape here. Now, if we think about it, one lone pair causes the angle to drop down by 2.5. If you've got 2 lone pairs, it will cause the angle to go down by twice as much. So that's 5 degrees. So 109.5 take away 5 degrees will leave you with, this is not going to be easy to put, 104.5 degrees. But all you do is you learn these shapes. The first thing you've got to do is just learn these shapes. Don't worry too much about understanding the reductions in the bond angles. That you do afterwards. You explain why the bond angle is reduced. But at the moment, it's just about working out the shape of the molecule. Now, I did also recently, one of my pupils asked me a question. Well, if you've got 4 electron pairs, what happens if you've got 1 bonding pair? And you've got 3 lone pairs? And I can't say I've really come across this, but I don't think you've really got many options. If you've got 1 bonding pair and I get rid of all of the rest of the bonding pairs and replace them with a lone pair, what I'll end up with is probably just an X that I've got with 1 bond, just a bond, doesn't matter which one, and a series of lone pairs that you've got coming from here. And that leaves me with this strange looking shape that I've got here. Really, it's not a shape anymore because there's not a lot you can see. You can't see the lone pairs. That's the crucial thing to remember. If I was to rub out the lone pair, which is what I'm going to do for you, that's the shape of that molecule you'd see. If I rub out the lone pairs, that's the shape of that molecule you would see. If I rub out the lone pairs, that's the shape. So if you think about it, all I'm left with is a straight line. That's linear in many ways. If we think about it, it's just a straight line. But that is really what you would end up drawing. So remember, you can't see the lone pair. I'm just going to put them back on because otherwise it looks like I've forgotten to draw them. And I'm going to move on to the next slide where I'll tidy this up for you a bit more. So here we go. If you have 3 bonding pairs of electrons, so 3 bonding pairs of electrons, this is a shape that I've been through, and 1 lone pair, you end up with this shape here. That's the one that I showed you. It might be drawn a slightly different way, but it's the same shape that we looked at earlier on. Remember, you can't see this lone pair. Okay, you can only see where the bonds are. The bond angle here is 107 degrees, and the shape is called trigonal pyramidal. Don't get confused between trigonal and bipyramidal. Okay, and remember the bond angle there is 107 degrees. What you should be doing is learning this template almost for 3 bonding pairs and 1 lone pair. So ammonia is our example we're going to look at. The central atom is nitrogen. So remember, we work out the total electrons. So nitrogen is in group 5 of the periodic table, plus the 3 hydrogens around it, so 3 atoms. Gets us to 8 electrons in total. It's not an ion. So then we take this answer 8, divide it by 2, and that gives us 4 electron pairs. Now, we've got 4 electron pairs. We need to work out if they are 4, if we've got 4 bonding pairs or we've got a lone pair in there. We need to work that out. So to do that, what we do is we work out lone pairs by taking this answer 4 and subtracting the number of atoms around the central atom. Well, that is 3. So take away 3 gives me 1 lone pair. So therefore, now it's a different story. Out of my 4 electron pairs, one of them's a lone pair. That must mean that 3 of them are bonding pairs. So I now have 3 bonding pairs plus 1 lone pair, because the total has to equal to the 4 electron pairs plus 1 lone pair. And that gives me this shape that I've got in the molecule in the middle, which is a trigonopyramidal shape. So I start by drawing my nitrogen in the middle. I can draw my wedge this side, my dotted line like that. If I copy that shape out, my line there, and draw my lone pair. I'll do it in red, my lone pair at the top like that. The bond angle, I'll put the hydrogens in afterwards. The bond angle there is 107 degrees. Okay, and that would get me my marks in the exam. Okay, I'm going to move on, and I'm going to do the next one, which we looked at with 2 lone pairs and 2 bonding pairs. So that gives us a bench shape. Okay, a bench shape, or you can also call it a V shape. Okay, so you can also call it a V shape because you've got this kind of lovely V shape there. So if you have 2 bonding pairs of electrons and 2 lone pairs, you'll get to this shape in the middle, where all I've done is taken the tetrahedral shape, the one with the 4 bonds around it, 4 single covalent bonds, and I've replaced 2 of the straight lines like you saw me doing earlier on with just 2 lone pairs. So it's 104.5. But we tend not to draw a 3D shape for this. Whenever we've got this bent V shape, we're happy enough if in the exam you put your central atom, 2 bonds to the left and the right, and put a lone pair there and a lone pair there. And that's much easier to remember. 2 bonding pairs, 2 lone pairs gives us this V shape or bench shape. And that's how I'm going to draw it. So water is your classic example of this. So again, we start by working out the total number of electrons by group number of central atom. And that makes sense. It's oxygen. Okay, so oxygen is our central atom, which is in group 6, plus the number of atoms around it. That's 2. So that gives me 8 electrons in total. It's not an ion, so I move on to the next step, which is 8 divided by 2. That will give me 4 electron pairs. Then I need to work out of these 4 electron pairs, how many are bonding pairs and how many are lone pairs. So what I will do now is to work out the number of lone pairs, which equals this answer 4. Take away the number of atoms around the central atom, which is 2. So that gives me 2 lone pairs. 4 take away 2 is 2. And therefore I write my conclusion. My conclusion is out of these 4 electron pairs, 2 of them must be lone pairs. Therefore 2, that leaves me with 2 which must be bonding pairs, because the total has to be 4. So 2 bonding pairs, and I've also got 2 lone pairs on there, and that total equals to 4 electron pairs. So if I draw my shape, I'm going to use this particular template here, where my X is my oxygen, bond there, my lone pair there, put a hydrogen there, and the bond angle in here is 104.5 degrees. I'm not going to go too much into these bond angle reasons or why that is the case, because that becomes almost a separate lesson as to why the bond angle is reduced. And like I say, recently someone came across and asked me an example of a molecule which has 1 bonding pair and 3 lone pairs, but I can make a separate video on more difficult shapes for you if you want me to. Okay, moving on. So that's your 4 electron pairs done. So what happens if we look at 5 electron pairs? So again, this is just a recap of the previous of a slide we looked at earlier on. I'm going to get rid of this. So this was based on 5 electron pairs. So this was the 5 electron pairs, and if we think about the combinations that we can get for 5 electron pairs, we'll be able to work out what we're about to see in the next few slides. So out of 5 electron pairs, we could get 5 bonding pairs, which gives us this trigonal bipyramidal shape. We could get a situation where we end up with 4 bonding pairs plus 1 lone pair. Okay, so we could get one lone pair like that. We could get a situation where we get 3 bonding pairs plus 2 lone pairs. That would work as well. We could get a situation where we get 2 bonding pairs and we get 3 lone pairs. So those are different possibilities. You could go for the extreme, which is 1 bonding pair and 4 lone pairs. I can't say I've come across something like that. But these are things to certainly think about. And what I'm going to do is certainly go through all of them. But one of them I'll create a separate slide for you, but I'll run you through all the bond angles that we get and the shapes that we get to. Remember, all we're doing is taking one of these and ripping off one of those bonds we've got, replacing with a lone pair. But you have to know which one to rip off and replace. That's the crucial thing, because we're trying to minimize the repulsion in the molecule. So let's have a look at this. Okay, so we're basing it on 5 electron pairs. If they were all bonding pairs, we'd end up with this trigonal bipyramidal shape. What happens if out of the 5 electron pairs, 4 are bonding pairs and you've got 1 lone pair? Well, you get this shape, which is called a seesaw, where I've replaced one of the bond with a lone pair. There is another way to draw it. There is a much easier way to draw it, which I'll talk you through in a minute, but there it is. I've replaced it. Okay, the much easier way to draw it is certainly if you think about this picture on the right hand side, and we think about what shape we'd had at the start. So that was my trigonal bipyramidal shape. If I wanted to make it easier, I could have just replaced this one here with a lone pair, which is going to be very similar to what I've got here. It's just the other way round. And what I would have got is X like this, like that, and my lone pair just there. That's not a very good picture. I'll redraw it. There we go, like that. Okay, that's what you would get. Now, what's important to remember is, as a result of putting this lone pair in there, the bond angles are going to be reduced. The repulsion between a lone pair and a bonding pair is much greater than just normal bonding pairs. So where we had the bond angle, which was 90 degrees before, and I'm just going to stick to this picture I've got here because I think it's easier to show you on here. Where we had 90 degrees, because this lone pair is put there, it's going to slightly push this bonding pair more, and it's going to reduce that bond angle to about 89 degrees. It's going to make it slightly less, 88 or 89 degrees. And if you remember, across the other way, it was like a circle, a full circle we had. But remember, we've now got this bond angle here, and you've got a lone pair where the bond was. That lone pair is going to repel these bonding electrons much more strongly, and that bonding angle gets reduced to 118 degrees. So that bond angle is less. Like I said, the focus should be you just learning the shapes, the bond angles, and making sure you can work it out. The explanations behind it can be looked at afterwards as to why these bond angles are reduced. So I'm going to keep concentrating on working out the shape that we've got. So sulfur tetrafluoride, we're going to start by working out the total electrons. So total electrons equals the group number of the central atom, sulfur. Group 6 plus the atoms around it, 4. That gives us 10 electrons. It's not an ion, so we take 10, divide it by 2, and we get 5 electron pairs. We then need to work out the number of lone pairs. So we do lone pairs equals this answer here, 5. Take away the number of atoms around the center, which is 4. That gives us 1 lone pair. Therefore, the conclusion we make from here is, out of our 5 electron pairs, we've got 4 bonding pairs. Okay, and we have 1 lone pair. So if we draw this particular molecule, I'm going to stick to this template in the middle. We've got sulfur here, up, down, across. There's my lone pair. There's a wedge for that bond that's coming out. Fluorine, 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 and fluorine. And then remember, I need to mark the bond angles. That's no longer 90. It's going to be slightly less, so 89 degrees. And then I'm going to go for, I'll do it in green, this angle between here and across there, and that's no longer 120. It's going to be slightly less, 118 degrees is fine, and that's my seesaw shape that I've got there. Okay, moving on, because the lesson is getting quite long, so if I can speed through the next part will probably save you a bit of time. So the next one's T-shaped. I'm sure you can see why. It looks like a T. There's the T you've got there. So there, and there. And if we just go for the molecule that we base it on, the trigonal bipyramidal, which looks like that, essentially we've replaced two of these bonds with two lone pairs. Now I've written on the bottom, the common mistake is to put the lone pairs opposite each other. So the common mistake is to basically do this. And some examples will let you off. That's the common mistake. That's not really the shape we get. There is a reason why we get T-shaped and we don't end up with this particular shape that we've got here. But I'm not going to go through that at the moment. Just don't put them opposite each other. Put them arranged like I have done here. Okay. So if we look at this molecule, which is chlorine trifluoride, the central atom is chlorine. So total electrons is chlorine, which is the group number of that is 7, plus the number of atoms around it 3. So that gives us 10 electrons. It's not an ion, so we then take 10 divided by 2, which gives us 5 electron pairs. So there it is, 5 electron pairs again. We then need to work out the number of lone pairs. So we do lone pairs equals 5. Take away the number of atoms around the center, which is 3. So that gives us 2 lone pairs. Therefore, the conclusion is after 5 electron pairs, 3 must be bonding pairs. So 3 bonding pairs plus 2 lone pairs. And if we stick to this template we've got, then our chlorine will go in the middle, up, down, across. We've got a lone pair here, a lone pair there, and this angle here is now 89 degrees. It was 90 before, but it's, remember, slightly less because of the lone pair. I'm just going to straighten that bond up because it doesn't look too great. There we go. Now, don't make the mistake of labeling this angle here because there is no angle. Remember, it's between two bonds. There isn't two bonds across that direction for you to draw an angle between. So don't please label that. Okay, before I move on to this one, I'm just going to insert a slide just to go through the other extreme that I wanted to mention to you, which is what happens when you've got two bonding pairs and three lone pairs, because I think that's very, very important to do. Okay, so to quickly cover that, that's the situation which we said if you have two bonding pairs and you have 3 lone pairs. Okay, I'm not going to worry about working that out too much. I'm giving you an example to illustrate that. I think when you get the example, you'll certainly get to this conclusion. So 2 bonding pairs and 3 lone pairs. If you've got 5 electron pairs, and let's just say this is something you end up with, then what you've got to remember is it's all based on this shape. It's all based on the 5 electron pair shape, because 2 and 3 gives us 5 electron pairs in total. What you do is you replace this, and that one. Okay, I've replaced with a lone pair. Again, there are reasons, and we can talk about the reasons in a separate lesson rather than this one because it's getting quite long. And what you end up with is you end up with X with a bond at the top, bond at the bottom, and this is a lone pair. And this one here is a lone pair. All the highlighted ones are lone pairs. So you end up with this. You don't see the lone pairs. All you see is where the bonds are. Don't just draw this, but that's just to illustrate what you end up with is a straight line, a linear shape, because you can just see where the bonds are. You can't see the lone pairs. Okay, so if you think about it, actually the shape you end up with is a linear shape, and the bond angle between this, the two bonds you've got, is going to be 180 degrees. And there are a couple of examples which have cropped up on the new spec exam papers where you do get a situation like this. So make sure you know about this shape. But the crucial thing to remember is if you end up with 2 bonding pairs, 3 lone pairs, then you've got a linear shape with a 180 degree bond angle. Okay, our last set, which is based on 6 electron pairs. So again, you've seen this one before, where if you've got 6 electron pairs, we end up with if they are all bonding pairs, we end up with this shape here, which is an octahedral shape, and I drew it slightly in a different way earlier on. So these were 6 bonding pairs. But remember, this is all based on the stuff we're going to look at. We're looking at 6 electron pairs. Okay, so that's what we're interested in, 6 electron pairs and what we get. In this case, the bond angle was 90 degrees, and the shape was an octahedral. But there will be different possibilities. You could get 5 bonding pairs plus 1 lone pair. Okay, so we need to look at that. We could end up with 4 bonding pairs. Okay, plus 2 lone pairs. And you could obviously carry on going and looking at the different combinations. These are the 2 most common ones that come up in the exam. They're the ones that I'm going to stick with. And if you obviously want me to do any other ones, any difficult ones, I will make a separate video on that depending on the feedback from this one. But anyway, let's move on. So if we take the octahedral shape that I drew earlier on, remember it was based on this principle here. So I had 2 bonds coming out, 2 going backwards and 2 in the same plane. If I replace one of these bonds, which I've just taken off the bottom one, I could have taken the top one off, stuck a lone pair there, what you end up with is this shape here, which is square pyramidal. Okay, so you end up with this shape here, square pyramidal. And the bond angle in this particular molecule that you've got is no longer 90 degrees because this lone pair at the bottom, and you end up with 89 degrees. So slightly less than what we had before. And again, if I do my calculation, so, well, I say calculation, my working out. So total electrons equals the central atom, which is, say, iodine in this case, group 7, plus the number of atoms around the center, which is 5. Then that will get me to 12 electrons in total. It's not an ion, so we do 12 divided by 2, gives us 6 electron pairs. And then what we do is we work out the number of lone pairs, which is this number here, 6. Take away the number of atoms around the center, 5. So we end up with 1 lone pair. And hence our conclusion is, out of these 6 electron pairs, 5 must be bonding pairs, and 1 is a lone pair. Okay, so one of these is a lone pair. And to quickly draw the shape, I'm going to base it on this template that you can see, where the iodine goes in the middle, bond up. We've got a wedge here, wedge there, a dotted line going there, dotted line going there, and a lone pair there at the bottom. And this bond angle here is 89 degrees, no longer 90 degrees. Okay. So moving on to our final example, because I think you've probably had enough by now. Our final example is square planar. Okay, a common shape when you look at transition metal chemistry. And that's based on 4 bonding pairs of electrons and 2 lone pairs. Again, think about your original shape you had. Look like this. All we've done is replace 2 of these bonds with 2 lone pairs. And although this is drawn in a nice 3D way, you can also draw this if you want to. Now I'm going to have to find some space for me to draw this. You could draw it as, if you want to, X in the middle, 1 back, just like this. You don't have to draw it like back and 2 going back, 2 going front. If you pick the molecule up and look at it from the top, it will look like this kind of cross that you've got. You can draw it like that if you want to. The bond angles in this molecule when you have a square planar is essentially 90 degrees. Okay, just like this is showing you here. But it's very important that you also show your lone pairs on that. I prefer to draw this one in the middle, so I'm going to stick to that one there, where there's a bond coming out and 2 bonds going in, so it reflects what you can see here, and then 2 lone pairs that you've got there as well. But the bond angle here is 90 degrees. That's the only bond angle in here. This is our last shape and the last one, I promise. Central atom is chlorine. So total electrons here is group 7 for the chlorine. Number of atoms around it is 4. So if we add that up, it's 11 electrons. But guess what? It's an ion this time. It's an ion with a negative charge. So if it's negative, we need to add an extra electron at this point. So that would be 11 electrons plus 1. Okay, it's 1 extra electron we're adding on there because it's a negatively charged ion. and therefore that will give us 12 electrons in total. So we need to pay attention to if it's an ion or not. Then we just carry on as normal. 12 divided by 2 gives me 6 electron pairs. Work out the number of lone pairs. So to work out the number of lone pairs, it's this number here, 6. Take away the number of atoms around the center, which is 4. This is 2 lone pairs. And our conclusion is that out of the 6 electron pairs, if 2 of them are lone pairs, that will mean we've got 4 bonding pairs, and we have got 2 lone pairs. And that will finally give us this square planar shape here, where our chlorine is in the middle. If I draw the rest out, oh, that's not good. There we go. Put a lone pair there, lone pair here, fluorine, 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 fluorine. I would enclose the whole thing in square brackets and put a minus charge, and that is the shape that we get. Okay, for that. Oops. I hope you've enjoyed this lesson. It's turned out to be about 50 minutes, but if you have, it'd be great to get your feedback and a few likes, and then I will certainly focus on making more lessons. But I hope you've enjoyed that. Thank you.